In the beginning, there was light. And I mean a lot of light. In the early stages of the Big Bang, the universe was so hot and dense that matter as we know it couldn't exist. Only an unimaginably intense primordial fire of plasma and radiation. When the universe cooled enough, particles formed, and then the first atoms. And for millions of years, as the light from the Big Bang dispersed, the universe became cold and dark, filled with a quiet fog of hydrogen and a bit of helium. So how did we go from this to this? Let's talk about cosmic dawn. The first star to form in the universe appeared somewhere around 100 or 200 million years after the Big Bang. At that time, gravity was just beginning to gather the slowly cooling fog of the primordial hydrogen-helium soup into galaxy-sized clouds. Inside these clouds, smaller clumps began to form, coming together due to their own gravity and forming protostellar clouds. But going from a protostellar cloud to a star takes a bit of counterintuitive physics. Before a star can form, the gas needs to cool down, and that's actually harder to accomplish in the early universe. Here's why. If you just compress a gas, it increases the pressure and the gas heats up. Higher temperature just means more motion. Gas particles moving and bouncing around faster. The trick is to somehow get the gas to both compress and cool down, so the gravitational force can overcome the pressure and hold it together. For that, you need the gas to radiate away its heat. Certain molecules, when they bounce around and collide, begin rotating or vibrating, or have their electrons pushed up to higher energy levels. This makes them like little rechargeable batteries, storing some of the energy that had been in the form of their motion, and allows them to later release the energy by emitting photons, particles of light. Those photons can then escape the gas cloud, taking the energy with them, which has the overall effect of cooling down the gas. This, incidentally, is how radiators work. The metal is heated, which is just a way of saying that the individual atoms start bouncing around within the metal, and then that energy is released as infrared radiation, which you feel as heat. But in the early universe, there wasn't any metal. The only elements that existed in abundance were hydrogen and helium. And that lack of chemical variety was a problem. Complex molecules and heavy elements have more ways to move and to shift their electrons around, which makes them much better at storing and then quickly dissipating energy than hydrogen and helium. The radiative cooling process, essential for star formation, is much more effective when the gas is just a little bit dirty. Because of that, we think the first stars were probably, on average, quite a bit more massive than most of the stars we see today. The clouds they formed from had to gather more mass to have enough gravity to overcome the pressure of that hot gas so it could come together. Once the gas was compressed enough, it was able to form a hot, dense core in which nuclear reactions could occur. Those first stars converted hydrogen into helium in their cores, and in later stages fused heavier elements together, making carbon, oxygen, nitrogen, and so on, filling up the whole periodic table over successive generations. Astronomers tend to call all elements heavier than hydrogen metals, so the more varied the chemical distribution in a star, the higher its metallicity. When the interstellar medium, the gas between the stars, gets sufficiently enriched with heavy elements, it becomes easier to form stars, and they look more like the stars we see today.
So in astronomy, we're at a bit of a disadvantage compared to a lot of other scientific fields because we can't take apart and manipulate the things that we're trying to understand. All we can do is look at them. And so we're lucky that the things we're trying to understand are actually simpler. So a star is much simpler in some sense than a frog. Both the advantage and the disadvantage are kind of amplified when we go to the first stars in the universe, where we haven't even seen these things. We just know that they must exist. But they're the simplest stars because they contain only hydrogen and helium. Because they're so simple, even though we've never seen them, we can try to build some models and have some hope of understanding how they might have worked.
The metals created by the first generations of stars weren't only important for cooling down gas to make more stars, they also became the building blocks of planets and of us. Those first stars set into motion a process that eventually allowed the Sun, the Earth, and the rest of the solar system to form, laying down all the ingredients for life. Carl Sagan once said, "The cosmos is within us. We are made of star stuff." And it's true. By weight, each of us is about 90% atoms that were formed inside stars or in the explosions at the ends of stars' lives. The other 10%, the hydrogen, comes to us unchanged straight from the Big Bang. Cosmology gives us the opportunity to study our origins, how we came to exist, and how the laws of physics created all the wonders we see around us. As Carl Sagan also said, "We are a way for the universe to know itself."